All right, so we're going to talk about center of mass and moments today. And Mr. Lowe is very excited because we're almost to triple integrals. He keeps asking if we've learned triple integrals yet.
I told him that we were learning double integrals.
Yeah.
Are we going to have to rearrange triple integrals?
Usually not. Usually not.
The right side is right side up and the left
Because
side is up.
triple integrals, they're easier in spherical coordinates or cylindrical coordinates, and usually you don't have to rearrange them. You set them up in spherical or cylindrical coordinates, and they're nice. Sometimes you might have to switch something in if you set them up in rectangular coordinates, but usually you do one integral and then you switch the order for the double integral. It's usually the way it works. All right, so last semester we came up with a process of finding the mass and the center mass of a planar lamina, a thin sheet in the plane, and our assumption was that our density was constant. That allowed us to do it with the techniques that we had last semester. Well, now that we know how to do double integrals, we don't have to make that assumption. So if we have I'm just going to do a quick sketch here of a region. And we have some region in the xy plane. And we have a little section of the area, and it's very small. It's dx this way and dy that way, and I'm going to put a little index on, so that's dx sub I, dy sub I. And we're going to say in this region that our density, our mass per unit area, is variable. So we're going to say rho of xy is mass per area. So the mass of this little section in my region here, m sub I, is just going to be rho of x sub I, y sub I times dx sub I, dy sub I. And if we want the mass of the entire region, we're just going to add up. We're just going to add up all these little masses. And this fits with our definition of a double integral. If we sum all these masses, this fits our definition of a double integral. So the mass over the region is rho times the area. And because our density is variable, this is just going to be the double integral over our region of rho as a function of x and y times dA. So we can find the mass if our density is variable. We can find the mass with a double integral. And rho of xy is just mass per unit area. Make sense? So we'll do some examples. We'll do some examples in a little bit, and we need to use our mass when we find our moments as well. So our mass is just a double integral. We're integrating the density function over our region. So our moments. To do moments with single integrals, we had to make a lot of assumptions. We assumed that our density, we had a constant density, uniform density. That allowed us to assume that the mass of each little segment that we're dividing our our lamina into was concentrated at the center. So we could find the distance of that mass from each axis using those simplifications. Now that we know double integration, we don't have to assume those simplifications. So for moments, we're going to use our same drawing. We have a region in the xy plane, and we're talking about a planar moments and center of mass of a planar lamina. So here's our little piece of this region, R, and its distance, it's at the center of this little piece is at the coordinates x sub I, y sub I. And our mass, just like before. Hi, Amelia. I was just telling them about our adventures in 7th period yesterday. Let me get your. All right. So this is our little piece of the region, and our mass, just like from what we just talked about, our mass is our density at that little at those coordinates. Delta A sub I. So times the area of that little region. And we're going to remember we defined our moment. Our first moment is the mass. We're weighting this mass by its distance from the axis, and we're summing all of those masses weighted by their distance from the axis to get our moment. So our moment about the x-axis is m sub I, y sub I. This mass weighted by its distance from the x-axis, and that is from our diagram here is just going to be rho of x sub I, y sub I times y sub I times delta A sub I. And our moment about the y-axis is that mass's distance from the y-axis, which is just x sub I, and we just get our density at that point times its distance from the y-axis times its area. And we're going to sum these moments to get the moment for the entire region. And again, this fits with our definition of a double integral. To sum all of these over the region is a double integral. So we call this the moment that we're working with now. We call it the moment. You'll see it referred to a lot of different ways. The moment of mass. Oh, I put too many letters in there. Or first moment of mass. All these things mean the same thing. And first moment refers to the fact that we're weighting it just by its distance. So our distance is raised to the first power. So the moment of mass, first moment of mass, with respect to our different, we do our moment with respect to each axis. So with respect to the x-axis, is m sub x, and that's a double integral over our region of our density function times y times dA. And about the y-axis, m sub y, and that is our double integral just weighted by its distance from the y-axis. Rho of xy, x dA. And our center of mass, just like we did before, we just divide our moment by the mass. And I'm going to use COM, so I don't have to keep writing center of mass. And our notation is x bar, y bar. This gives us the coordinates of our center of mass. We divide for the x-coordinate, we divide the moment about the y-axis by our mass, and for the y-coordinate, we divide the moment about the x-axis by the mass. Yes?
So this is only two-dimensional?
Yes. When we talk about triple integrals, then we'll talk about a solid shape and finding the moments and center of mass of a solid shape. Now, when we talked about this before, we talked about the centroid of a planar lamina. Centroid, and I think I mentioned it before, centroid usually refers to, we're talking about a planar lamina with uniform density. So a centroid is a property of the shape. It doesn't depend on the material. Here, because we're letting our density be variable, we usually refer to it as a center of mass because it's a property of the it has to do with the shape and the material. So the centroid is a property of the shape. We're assuming that the density is uniform. Here, our density is variable, so we call it the center of mass. So just a distinction between those two terms. Questions on how we come up with these? It's pretty straightforward. We're just plugging in our density function to find our mass, weight that mass by its distance from a particular axis to find our moments. Okay? Let's do a couple of examples, and then we'll talk about a second moment. And if you want to get Mr. Grace engaged in some interesting mathematics, they use third moments in statistics. You could ask Mr. Grace about third moments. So I couldn't think of an example where we use third moments in physics or in science, but I know they use third moments in statistics. It has to do with the distance, with how far something is from like a central tendency or something, and you use it to calculate something. All right, let's look at a mass integral for mass first. So we want the mass of the planar lamina we have our region is bounded by x greater than or equal to 0 and 0 less than or equal to y less than or equal to 9 minus x squared. And our density, rho of xy, is x times y. So we want the density of this planar lamina. So let's sketch our region. what is this region going to look like?
A quarter of a circle.
Quarter of a circle, right. And this is y equals 9 minus x squared. So we can, so how do you want to set up this integral? Want to do vertical? So we want to do, we'll do it this way. So vertical rectangles for a representative rectangle. So our mass is going to be our integral y equals, y equals 0 to 9 minus x squared. X equals 0 to 3.
Shouldn't we get rid of 9 minus x squared? That's not a circle.
Oh, let's see.
Is it parabola? Or secant parabola?
Yes, this should, you're right, that should be root. And so x equals 0 to 3. Y times x. We can do xy, doesn't matter. xy dy dx. And we would evaluate that integral.
Wait, but then don't you multiply it by? Oh,
So we're just finding the mass here. So this is my density function, dy dx. And this one is not too bad to evaluate, not terrible. But is there another way we could do it?
the other way.
We could do it horizontal rectangles, or we could do polar coordinates. So for polar coordinates, our mass would be integral theta varies from what? 0 to pi over 2. R equals 0 to 3. X times y is r squared sine theta cosine theta. R dr d theta. I think this one's going to be easier. This one's pretty easy. But either way, you can do it either way. If we evaluate this out, either way you evaluate it, it should be fairly straightforward. So I'm just going to set these up. I'm not going to evaluate them. So that's our setup for finding the mass. So let's look at finding the mass, finding the center of mass. What we need to set up to find the center of mass. Questions on that example? Okay. So we're going to find the mass and center of mass. So we're going to set up our integrals for mass and center of mass. And our region is bounded by y equals x to the third, y equals 0, x equals 2, and rho equals some constant times x. So we need to set up our integrals to find mass and center of mass. So let's sketch our region. Here is y equals x to the third. Here's x equals 2. So our region is in here. So our mass. To find our mass, we have a double integral. How do we want to set up our double integral here? You want to do horizontal?
Should I check on mine?
It really doesn't matter. So we want our rectangles this way.
Oh, I'm at vertical.
We want to do vertical. Change our mind. Okay. It's about the same either way. So y equals 0 to x to the third, x equals 0 to 2. We put our density function in, kx dy dx. Not a difficult one to evaluate. If we evaluate this, it turns out that our mass is 32k over 5. Our moment about the x-axis. We've set up our integral. Our limits stay the same, so we can just put this in our integral. We found our region, and we just need to we need to weight this by its distance from the x-axis. So we get kxy dy dx. So that would be our integral for the moment about the x-axis. When we evaluate that, we should end up with 16k. Not a difficult integral to evaluate. Our moment about the y, we have our same region for our integration. So integral 0 to 2, 0 to x to the third, and we're weighting this by the distance from the y-axis. So we get k x squared dy dx. And we integrate, if we evaluate that, we come up with 32k over 3. And our x-coordinate of our center of mass is m sub y over m, which gives us 5/3. And our y-coordinate is m sub x over m, and we get 5/2. And it's always a good idea when you're finding your mass and your center of mass, when you end up with your coordinates, to make sure they make sense in terms of your region. Because if we got an x-coordinate of our center of mass as 2.5, we'd know we did something wrong. If we got our y-coordinate as 3, we'd know we did something wrong. So you need to make sure your center of mass is, it's a good idea to just check to make sure your center of mass is inside your region. And because there's a lot of repetition here, what I do on tests with some of these things is I'll say set up but do not evaluate the integrals to find the mass and the center of mass of this particular region, because there's a lot of repetition and a lot of evaluation of integrals. And the important thing is to know how to set them up. Questions on that? All right, now we can talk about second moments. So for our first moment, we weighted the mass by its distance from the x or y axis. For the second moment, we weight it by the square of the distance. So everything that we said about setting up our integrals and how we evaluate them, how we come up with the expression for the second moment is exactly the same. We're just weighting it by the square of the distance. So instead of putting x into our integral, we're going to put x squared into our integral, and that would be the second moment about the y-axis. Instead of y, we're going to put y squared. That's going to be the second moment about the x-axis. The other thing, that the name that you usually hear, that you'd be more familiar with for second moments, is moment of inertia. So in physics, you use second moments to talk about moment of inertia, and it's a measure of the tendency of a mass to resist a change in rotation. And following the same line of reasoning that we used for first moments, we're going to say that I sub x, and I stands for moment of inertia. I sub x is the double integral over our region of y squared times our density function over our region. And I sub y equals a double integral over our region of x squared times our density function and then we have a third one here that we call I sub 0, and that's the sum of the moments about the x and y. And that's the integral over our region of x squared plus y squared times our density function times dA. And we could also write this as the double integral of r squared. And I sub 0 is called the polar moment of inertia. Or the second moment about the z-axis. So the r squared just measures its distance from the origin, and in the plane the origin is that's the same as its distance from the z-axis. So I sub 0 is just the sum of I sub x and I sub y. We set them up, we evaluate them just the same as we did our other double integrals. Questions on that? All right, one other term that you need to know that has to do with moments of inertia. The radius of gyration. We call the radius of gyration r double bar. And we define that as the square root of I over m. And what the radius of the gyration tells us is that if we have a mass that's rotating about an axis, if the mass is rotating about an axis, and if the entire mass is concentrated at this distance, it would have the same moment of inertia as the entire system rotating about the axis. So the radius of gyration just gives us a way to, if we have a rotating system, we can simplify our calculations by calculating the radius of gyration, and we can assume that the mass is concentrated at that distance from the axis. And with certain types of problems, with certain types of calculations, it simplifies the work. So we have a radius of gyration. We defined it as the moment of inertia over the mass. We have a moment of inertia about the x-axis and about the y-axis. So depending on our axis, we'd say r sub x, or we can say x double bar is the square root of I sub y over m, and y double bar is the square root of I sub x over m. All right, are we good on that? Do we need to see any examples of calculating second moments?
Yes.
Yes, no? All right, let me pick out a good example here. All right, let's look at this one. So we want to find, we're going to set up the integrals that we need to find I sub x, I sub y, I sub 0, x double bar, and y double bar. And our region is bounded by y equals x squared, y squared equals x, and our density function is x squared plus y squared. So we're just setting up our integrals here. We're not going to evaluate them. So let's sketch our region. There's y and x. Y equals x squared is here. Y squared equals x is here. So our region is in here. And what's our intersection point here? 1, 1. So our integrals, we can set up our integrals now. How do we want to set them up? Vertical? That would be my choice. So our mass is the integral y equals x squared to square root of x. X equals 0 to 1. And we put our density function in, x squared plus y squared, dy dx. Now we have our integrals, our region set up for our integrals. We can just plug in what we need for our moments. So I sub x is the integral, same limits. x squared plus y squared, and we're weighting this by its square of the distance from the x-axis. So that's going to be y squared. I sub y is the integral, same limits, 0 to 1, x squared, square root of x. Our density function, x squared plus y squared, weighting by the distance, the square of the distance from the y-axis. So we're going to plug in an x squared, dy dx. And I sub 0, our polar moment of inertia, is just I sub x plus I sub y. Once we calculate these two, we have what we need for our polar moment of inertia. And our x bar, or x double bar, is just going to be the square root of I sub y over m. And y double bar is just going to be the square root of I sub x over m. So this would be our setup. Questions? If you know how to set up double integrals, if you know how to figure out your region, this is pretty straightforward. A pretty straightforward extension of that. We're just putting in our density function and weighting our mass by its distance from an axis, first moment, second moment. But yeah, if you want to ask Mr. Grace about third moments and where you use them in statistics. Okay. Homework. There you go.